So today I will talk about learning visual representations, and so how we learn them from internet videos. But really, what we like to do is to then use them sort of to learn models which could sort of interact with the real world, act and interact with the real world. So you will see at the end some examples towards that. And this area is really exciting because visual data is all around us. Aircraft of visual informations, they store internet videos, TV channels, or historical imagery. And cameras are all around us, from surveillance to car or personal cameras. And what I find particularly exciting is that all these data sources and devices, they record experiences of many different people from many different places over long periods of time, and then they begin to form what you can call collective or emerging collective visual memory. So, but imagine if we could learn from all this data. Imagine what if we could build machines that learn from this data by observing people, for example, how to perform complex manipulation actions, to create robots and assistants that help us with tedious manual work, or which can operate in dangerous environments where people cannot go. Or what if we could learn from past visual experiences to help localize and navigate in changing conditions for autonomous driving or mobile robotics? And I will be showing examples in this talk of work in this direction. And this talk I will structure around 3 scientific questions, which I believe are really important towards achieving these goals. And start with the first one. Well, what is the right visual vocabulary? So initially, sort of back in the old days, people thought that you could actually manually design rules to recognize individual objects. However, this proved to be very difficult because the appearance of an object, can vary a lot. For example, how would you define the appearance of a chair? Just seeing these examples. So really, what we are using all now is, and what works very well, is statistical machine learning. So we need 3 ingredients typically. We need training data, we need an image classifier, and training procedure. So many of you are using this all the time. And so more formally, what we are doing, we are trying to train or learn a classifier F, which takes some input images with labels Y, input images X, and we optimize over parameters of that classifier in order to minimize some loss on the training data, where this is the sum of individual losses on individual examples. Typically, we usually have some regularization to restrict the space of classifiers, but I will not talk about that much in detail. And in practice, we typically use millions of annotated training examples, or often we use classifiers with millions of parameters, and we require powerful training hardware, and still the models can take days or weeks of training. So you probably see by looking at this what one of the key problems is. So where all this data is coming from. So we assume in this setup, in this supervised learning setup, that we can collect all the training data. And this can be really tedious and time consuming. So here on the left, you can see an example of an image where there were individual chairs annotated in that image. So someone had to go in and annotate all these boxes. But this annotation is sometimes even ambiguous. If you see an image of that, this could be annotated. What is it? Is it a table, or is it a desk or bench? So it's expensive and it's ambiguous. And in video, this is even more amplified. For example, what is the set of manipulation actions that can be done with a particular tool? Or what is the set of human behaviors that correlate with pedestrian accidents? So even if you wanted to annotate stuff, so you would know, it would be difficult. You wouldn't know how to do it necessarily. So in contrast to language, where often the vocabulary is rather well defined, in the visual domain, the visual vocabulary is large, a priori unknown, and often dependent on the task. So the solution to this, and I think this is beginning to be fairly widely accepted, is that we really need to learn without human supervision, or we need to design methods or machines which can learn without annotations by people, by humans. So this is, in general, I think this domain is now called self-supervised learning, and it has several different flavors. So one can imagine really kind of an unsupervised setup where you have just images or just videos and you wish to learn some representation. Or a weakly supervised setup where you want to learn from the video or visual signal together with all available metadata, which could be video with text or speech or audio. This is often or sometimes called now cross-modal self-supervised learning, when one would like to learn from these different modalities together. Or one could even imagine learning by interaction with the environment, where the machine would interact with the environment and learn from these interactions. In this talk, I will focus mainly on this weakly supervised learning setup, where we will be learning from the video together with additional metadata. And the domain where I will focus mainly is the domain of instructional videos. So what is an instructional video? So here is an example. Imagine that you get stuck somewhere so far from civilization with a flat tire on your car, but yet you still have your mobile phone and you can Google how do I change car tire. So what you would get is a video like that where someone is really showing you with how to use the different tools to perform the task of changing car tire, which has its individual sub-steps, and talking about it. It's together as a video signal together with narration, with language, natural language. And if you're not happy with one video, there are actually many others with different tools and different models of the car. And in fact, there are really millions of these videos online for different domains like cooking, gardening, or healthcare. So this is a really exciting data source, and the setup which is interesting is, imagine that we could go and from this data learn some kind of an instruction manual automatically, so that we can then upload that to some machine or a robot and perform the same task in a different environment, or give someone else automatically instructions in different environment. One of the first our work in that area was addressing the problem of learning the sequence of main steps of a task, given a set of instruction videos of a task. For example, here changing the car tire. So here the input are two videos, the video signal, the narration, which is transcribed, and what we wish to learn automatically is the sequence of steps to achieve that task, together with localization of these individual steps in the narration and the video signal. Like to learn the steps and localize them in the video and the narration. And this is difficult because the same step can be expressed in very different words, different sentences in the different videos, like here. And at the same time, people can perform the same action in very different manner. So here the one person is doing the same action and sort of losing the bolts on the car with using the foot or the hand. And so the way one can formulate this problem of weakly supervised learning is, so we have the input is the video and the narration, yet what we would like to do is localize the individual steps, the individual actions in the video. So on a higher level, what we do here, so the narration is the language narration is Y, input video X, and so what we introduce is a latent variable Z, which is really which is solving the task which we want, is to localize the individual steps in the video. And we optimize over both the parameters of the classifier, which predicts the step locations, together with the individual locations in the video. And this would be under constraint. So to constrain it, we will relate the latent variable Z with the narration using constraints. So we have to formulate these constraints, how the actual task which we care about, which is captured by the latent variable Z, is related to the metadata Y. In this case, it's in this example, it's simple linear constraint. It usually is a bit more complex. These constraints can be complicated. So the challenge then becomes, what is the appropriate form of these constraints for the different problems, and how do we efficiently solve the problem? So I will not go in much more detail. This is sort of fairly high-level representation that it's similar to what we saw before, supervised learning problem. We have a loss on the data, regularization, but in addition, we have the constraints which relate the metadata Y to the actual task which we want to solve, which is captured by this latent variable Z. And here as an example, and this idea will be sort of reappearing later, this is an example of the output where given this is the individual steps automatically learned from video by analyzing the narration, and on the bar is the location of the individual action. So here loosening the bolts, for example, in the video. So this work has been applied on a relatively small scale. Of the input would be tens of videos of one particular task, like changing the car tire. And we would, in the data set for this work, we would have in order of 5 to 10 tasks, and later on a follow-up, maybe 50. But really what wouldn't be exciting if we could really scale this type of learning, weakly supervised learning, to sort of large amounts of instructional videos downloaded from the internet. And for this, we turned to WikiHow, which is a website which you may know, which really contains these instructional manuals for a variety of tasks, from how to make an ice cream, how to change car tire, or how to fall in love. But of course, because we work with visual data, we wanted to restrict the domain to more visual tasks. So what we did, and that was the kind of only manual annotation, if you wish, for this data set. We sort of manually curated sort of 23,000 different tasks which are visual. So where the person who is talking is describing something which is happening on the screen rather than something abstract like how to fall in love. And they are in, yes?
So before you move on, so I just want to remind the audience that they can use the Q&A box to ask questions during the presentation. And at the end, we're going to aggregate all those questions and ask them to Josef. So please go ahead, Josef.
Yeah, so for the questions, please enter it as Fabian described, and we'll have a discussion session at the end. If you stop hearing me, Fabian, or something goes with the presentation, please sort of tell me or let me know, because otherwise I just I don't see, I just see my screen here.
Sure thing.
So we've collected this data set, and we want the data set to be visual, and it contains several different sort of domains, from cooking, gardening, car repair, or sort of home doing so home repair tasks. And in total, there is 130 million clips. These are sort of short clips of few seconds, which are sourced from more than 1 million videos. So just to sort of compare to the size of the data set to existing data set of videos annotated with natural language. This is the list of the data set, this number of clips, captions, and number of videos. And so this data set is basically much bigger than anything else which is currently available. The difference is it's been automatically collected. So the language, the captions, if you wish, are obtained automatically by speech-to-text software. So there may be noisy, and I will show some of the problems with the noise in the data a bit later. So it's 3 orders of magnitude bigger than what is available almost. But some of these data sets have actually manually curated captions, where people actually look at the video and describe what's happening. In our case, it's automatic from these instructional videos. And in the first task, instead of defining explicitly some kind of a vocabulary of actions or steps, as we did before, instead we opt for learning embeddings. So this is an interesting and I believe is one of the ways forwards. Instead of trying to define some kind of fine-grained vocabulary, use a directly embedding and use the natural language as a representation, which is naturally compositional. The question is, of course, what's the actual representation of the language, and I will come back to this later. So the goal is then, given the data set of video and captions, here this is automatic transcription, what the person is saying when doing or showing the task, is to then, so we would have a video network which extracts a representation from the video clip, some kind of a descriptor, and a language text network which extracts a descriptor or representation from the caption. And we would like to learn those. So in this initial work, these are some pre-extracted fixed feature extractors followed by a shallow embedding network, which is learned, so that the captions of the same video and the caption from the same video is, or clip, is close in that embedding space, and caption video clip pairs from different videos are far from each other. I will show you an example of a loss later, but that's the intuition. And so in this first simple example, where we have a large data set, fixed feature extractors, just learn a shallow embedding at the top. What we can do is now we can write a language query and find the top, find in the data set, in that embedding space, the closest, so you have top 4 closest clips. And this is how it would look like for a language query, for example. Play here for a query glue. You would get, these are top 4 clips where someone is gluing something. If you put a variety of objects, if you put glue wood, you would see people gluing different types of wood as the top 4 retrieved examples. If you use cut wood, you will see different types of videos where someone is actually cutting wood. So you can see that we sort of naturally are extending by using this language embedding the vocabulary of target vocabulary. Cutting paper, you will see someone cutting a paper. And if you type in cut paper in circle, you would see actually someone cutting paper in circle. So this embedding sort of is naturally compositional representation defined by the language, even though at the moment the language representation may be quite simple. So this is just an example of a qualitative result. How would that look quantitatively? And this is studying on the x-axis so if you increase the size of the training data set to learn that embedding, would be a sort of retrieval performance on different data sets. This is on the cross-task data set. If you again use language query and you want to find what percentage of queries you found correctly, this is on the, and so green is cross-task, on MSRVT it is another video language data set. You can see the performance with more training data is getting better. So as we somewhat naturally expect. And what's interesting is, and I want to focus here on the UCOOP data set. So this is data set of cooking videos, and this is the light blue curve here. So more training data, noisy. So we're talking about this noisy data from, but automatically obtained from the How to 100 Million data set. And this horizontal bar corresponds to using the actual data available in the UCOOP data set, the training data to train the representation. So this was manually provided, so it's a supervised setup with manual annotation. So you can see that at some point, here will be sort of tens of thousands of manual annotations, so relatively small number, but at some point we can outperform the method train or embedding train for manual annotations using a large number but noisy annotations obtained automatically from these uncurated instructional videos. So this is exciting because now weakly supervised method is outperforming a fully supervised counterpart. I'll show you more examples like this later. So this data set is available online. So we have to download it from YouTube, but the links are online and the pre-trained models are online. You can try the demo on the website. So in this, in the work so far, what we had the video representation was pre-trained and fixed, and the language representation as well. And we were just learning the top layers. In the follow-up work, which is appearing at this CVPR, what we would like to actually do is to learn the video representation from scratch on this large-scale data. So the question you're asking, can we actually learn such a representation from scratch on this data without requiring, for example, ImageNet for pre-training as is usual, or kinetics for pre-training a video representation? And the way we will achieve that is that the language representation will be partly pre-trained, partly fixed, but we'll train this from scratch. And what we'll see, we'll design a new contrastive loss, which will be able to cope with some of the noise in the training data. So just to illustrate what kind of noise in the training data there is, so this is a video from the how to 100 million data set. And so you can't hear the sound, but I'll also play again. This woman here is talking about what she's doing, and here is automatic transcript of what she's doing. She's talking about spinach, then she's talking keep it simple. Maybe you can add fresh herbs, maybe oregano. You can add some other things, possibly, and then you give it a couple more tosses. So she's talking about it, and this is automatic transcription of that. So what we can visualize that clip again, where we show the fragments of the automatic transcript on the right, and you can see that only some of it is relevant. She says the spinach is relevant. She's doing spinach, which is happening to this particular video clip, and the verb here tossing is relevant. But actually, these things she's doing, maybe you can add them. They are actually not happening in this particular video. So we would like to, and this could be a problem, because if you say you only consider the one of these, for example, this one as the annotation, it will actually not correspond to what, it will not happen in this, it will not be happening in this video. It will be an incorrect, wrong signal here. So we'd like to have a representation which can deal with this type of a misalignment or noise in the training. And in detail, in a bit more detail, what we design is a multiple instance learning objective where, so again, we want for a given video, extract a representation here, and then for the different fragments, extract a representation here, put them in the same embedding space. But here, we would like to sort of put closer together only the most relevant fragments of the narration. So as you kind of maybe hear from on the slide, is that there are sort of multiple different candidates, and then so we sort of put close together in the embedding space only the most relevant. And those which are not relevant, they are not necessarily sort of moved close together in the embedding space during learning. So it's kind of a multiple instance learning objective where we consider multiple different candidates during training, and sort of give you a bit more detail on how this is happening. So we compute a similarity between video X and narration Y by the exponential of their dot product. Next, so we have a back of positive pairs, which are the ones coming from the same video as you saw before. And what we do, we contrast those positives with negative narration pairs, which are coming from different video clips, video and narration pairs. So what's key here, that we sort of sum over different positive, so different candidate positive pairs in that objective, compared to just considering a single possible example. And so here, just to illustrate, so the positives, so the back of the positive pairs, they are coming from the same video, the different narrations as we saw before, and the negatives are coming from different video narration pairs. And we optimize over both the learning, the video representation, and only part of the language representation. But the video representation F can be learned from scratch in this example. And here are, so this is how the network, this is how the language networks looks like, and this is how the video network looks like. I will not go much into details of this, but there is some kind of a feature extractor here together with an aggregator. This is just a max pooling over the separate words of the language fragment, so of embeddings of the individual words. And there's a linear embedding at the very top. And for the video, there's a feature extractor, like a 3D CNN for video. And again, there is a embedding at the top. But here for the video part, we can learn the entire network from scratch. So here I will sort of can maybe discuss details of the question. I will not go much more into the details. And we show in the paper also that having this kind of multiple instance contrastive loss is important to deal with the noise. And we show ablations for this. But I will directly jump and show you some of the results of this. So we actually evaluate this method on several different downstream tasks. So on action recognition of the two most commonly used data sets, on action localization, again, on several of the common data sets for this task, and different domains, just generally YouTube videos as well as instructional videos, and as well as on text-to-video retrieval. So these would be video and language caption data sets. And these are some highlights of the results in the paper. There is much more, including ablations. So first of all, this model obtains state-of-the-art results, or at least at the time of submission. Of course, things are moving quickly. On the compared to other self-supervised methods for learning video representation. So here are some of the competing methods, and this is our method obtaining the best results on action recognition on UCF and HMDB datasets. The other interesting experiment is that this representation can outperform, in some cases, the fully supervised counterparts on some of the downstream tasks. For example, on MSR-VTT, this is this video language retrieval, on the cross-task data set, or on the YouTube 8 million data set. The representation, even if you train on the data directly, on the data for that particular downstream task, here, pre-training on this weakly supervised but large-scale data set can outperform the fully supervised method trained only on the target task. And here is an example of, again, on the text-to-video retrieval, just for people also, we pre-train the representation on the how to 100 million data set, and then take that representation and take this set of test videos, extract the representations, and then put them in the common embedding space. At query times, we extract again from the given, we type the query at query time and extract representation of that query and embed that in the same joint embedding space and find the most relevant, or top n most relevant clips. So that's how the retrieval works. In this case, for the query someone is fishing, one can find video like this, for example. And this can be done in this what's called zero-shot setup. So in that case, we only pre-train on the how to 100 million data set and use the pre-trained representation for the retrieval on the target task. So we have not seen any training data from the target task. And this target task in this case is retrieval on UCOOK2. So this is an instructional video data set. And we just sort of embed the videos and captions from the test set and use it in the test setup. So this is performance of different representations. This is image representation pre-trained on ImageNet and kinetics. This is just pre-trained, so it has not seen any UCOOK data. So this is the performance. If you fine-tune that representation on UCOOK, you get this. And so they pre-train on ImageNet and kinetics, and then you fine-tune on UCOOK. And then if you just train on the how to 100 million data set, and then you apply directly with any fine-tuning, and you obtain this performance, which is sort of outperforming these other setups. So this is great. This is really sort of outperforming these methods. So the node here is that the UCOOK data set is instructional videos in the cooking domain, and it's true that the how to 100 million contains many cooking videos as well. So the domains are close, yet there is no overlap between the data set, but the domains are close. But one can get this quite significant improvement in this setup. So all the models are available online. So these been trained from scratch on this large data set. And we are preparing also a training, so parallel training code for this, which should be online. Maybe it's even online now on this website, or will be online very soon. I think it's almost ready. So that was sort of the first part, was this weakly supervised learning. And I will also, in the remaining time, I'll try to give you some examples of our work on these other two questions, which I believe are also very important. So the second one is about generalization. So I think it's really actually a fundamental problem. How do we design representations which generalize to different conditions and situations? And here, just to illustrate that, we would like to have a representation which, for example, as you saw before, can recognize the same action when it's performed very different ways, or can recognize the same action when it's captured from very different viewpoint or under different illumination conditions. More formally, in that setup, which we saw before, where we had loss on the data, maybe the sub-metadata in form of constraint, really what we are looking is what is the appropriate form of that classifier, which can capture the image variation, can be learned from few training examples. So now the widely accepted representation is some form of convolutional network represented for images and videos. For 3D objects, it's still quite up in the air. What is the right representation? And for video, there is still a lot of ongoing work on the different forms and architectures for video. I want to show you some examples of our work in this direction of generalization on slightly different problem of localization. And in this case, so here, but I think it's interesting as an example where there was these representations were sort of designed for one type of, in this case, imaging conditions, but were sort of found to not work very well in other ones. And I think this, and one sort of had to put additional work into designing representations which can overcome these problems. So we actually even set up a benchmark data set or sort of several data sets and a challenge. So there will be a workshop on that challenge, which is going to be happening on Monday. One of the tasks is related to autonomous driving, and it's about localizing the vehicle on the road. And of course, here there is a 3D model typically available, and the goal is given imagery from the car to localize the car with respect to that 3D model. And while it looked for some while, this problem is basically solved, that one can just localize the car fairly accurately. It turned out that if you want this worked well in typically in daylight condition, if you want to do that in say during night or in rainy condition, it works much worse. So there's a lot of work happening in this. Another related problem is on localization indoor, where typically there is a robot which may be going around in these inside a building, maybe a hospital, and the goal is to localize, given a 3D map, localize the robot accurately in that building, given sensors, typically images, that robot, and recover the precise camera position with respect to the given 3D model. And this is again challenging because in this case, the environment can change over time. So we need, again, representations which can overcome these issues. Like here, this is the same room in different times of the day. And again, here, changing environment. So this is an example architecture which we've designed, improved over time to address this, and it's really, this is about learning correspondences between images, and again done in this weakly supervised manner. So where we would like to, we don't have supervision on the individual correspondences. So in the video, we'll have typically supervision on the video level, but not on the level of individual actions or localizing them in the video. In this case, we have supervision on the level of images, but we don't have supervision on the level of individual correspondences. And again, we have to design representations and losses which can deal with this issue. This is a representation where the input are two different images, and here we construct what we call a correlation tensor, which sort of captures all the possible correspondences between those, and then sort of learn patterns of correspondences between from training data, which is related. We call it neighborhood consensus network, and it's related to neighborhood consensus constraint from multi-view image matching. And again, this using such representations, which can be learned from data, to overcome these changes in imaging conditions or in conditions, it can work significantly better than sort of the previous one. As an example, this localization accuracy And this is how often one localizes, how many queries one localizes within that accuracy. And this is sort of some work few years back, which is using more sort of standard tools, and one can improve on top of that using learned representations, which learn to generalize across these different conditions and situations. And some of the latest work is even here, which is actually on archive already. I should have cited the archive. So this is an example of work in where we wish to really generalize to new conditions and situation. I think in video, this also we need to design represent explicitly address this. And finally, I want to talk in the remaining about 10 minutes. I want to talk about a third very important question, which we not only want to identify or recognize individual entities in the video, but also actually sort of interpret what's happening in the video and reason about it. I think, of course, what is reasoning about the video content? One can have sort of very different ideas what it means. What I will show you is examples of reasoning about the physics, or can we actually have some physical representations of what's happening in the video? So there are. So this is an example of work in the direction where the input is an instructional video here, but it's not a long video. So here, this is a short clip of that video. So this work is still happening on a relatively small scale. So, but yet is extracting much richer representation from the video. We still work on scaling that up to the scales which you saw before in the previous part of the talk. So again, the input is a instructional video clip from an instructional video, and what we want to do as output is to have a 3D interpretation of that motion, and so this is a trajectory of the person's joints and the tool together with, and you can see the yellow arrows are the output and estimates of the actual forces between the person and the ground and person and the tool. So this is really kind of a physical representation of interpretation of the video, including not only the 3D trajectory, but also the actual contacts and forces, estimates of contacts and forces. I'd like to get it from a single video. And here is the sort of brief outline of the work. So we input video. We would like to, what we call a recognition stage, where we extract 2D entities from the video. And this would be a human pose. This would be key points on the tool and segmentation, and as well as recognizing contact states. So that would be here in green are joints which are in contact with the ground or the tool. So, and in red are joints which are not in contact. And we build a recognizer which can do that, which can recognize that the joint is in contact or not based on training data. And given this output of the recognition stage, we have then an estimation stage where we come up with a reconstructed 3D interpretation, which is really a trajectory, is a motion as well as control, the actual forces, estimates of the forces which generated that motion, but which explain the 2D inputs correctly from the video. And finally, we would like to then go and transfer these motions to robots. And so this is really ongoing work. I will just show you at the end, if I have time, just a sort of a step in the direction. To just show you some of the results. So this is the output of the 2D recognition stage, where we have the joints on the person as well as on the tool. Here is another example of a different action. Here, a person showering, and finally is another example of the person lifting a barbell. You can see that these are noisy, but sort of they are outputs of so well-tuned and trained algorithms on this data. I can give you maybe details in the discussion if someone is interested, or they are in the paper. And so in the estimation stage, this is reformulated as a optimization problem where we wish to we optimize over X is a configuration of the person over time, a trajectory of the person. U is the control, are the exerted forces, and C are the contact positions on the tool and on the ground. So we optimize over all those, and the objective, which is sum over the human, the person, and the tool, And it's a, so then sum over time, so the whole trajectory, and the loss is, the objective is that the 3D interpretation, when we project it to the image, should have low projection error. So this is like a reprojection error type objective, but subject to constraints which include a contact motion model, full body dynamics, and also constraints on forces. I will not go into details of this, it will be another separate talk, but it's really formulated as this optimization problem with constraints. Instead, I will show you some results. These are, we have two data sets, a data set of YouTube videos, which you downloaded online. This is from YouTube, which of different people interacting with different tools, as well as, but we don't have ground truth for this. But this is really what we would like to show we can solve and transform a robot. But to validate the model, we have a data set of, which is called parkour data set, which has a mocap where you have a person interacting with this, with object doing these parkour actions. And for this, we have ground truth motion and forces coming from separate sensor. So we validate the model on this data, and then I will show you, but I will not show you in details of this, but I will show you now examples of outputs on the YouTube videos. So here, this is the input. These are the 2D output of the 2D recognition stage, and this is an example of the 3D output from two different viewpoints. The yellow arrows are again the estimates of the forces. And here, to get the estimates of the forces, I didn't talk about it, we assume some kind of a general sort of mass distribution of the person, and then some sort of rough estimate of the mass of the object. And here are some more examples of some of the videos. I'll sort of skip through this fairly quickly. There are these different hammering motions. We have a scythe as another object. You can see that the ground can be even tilted. So skipping through this, the video is online for Spade. What's interesting here that we really model the interaction well with we model the interaction between the person and the tool, but we do not model at the moment the interaction between the tool and the ground. And in some sense, for robotics applications, that's what is interesting. But this is, of course, much more difficult to model these type of interactions. But this is something which we are looking at the moment. So really, this is kind of leading to the last. I'll show just a little bit in the direction of acting on the world. So we wish to really learn these representations from videos, either on a large scale, and which can also perform some kind of at least physical at the beginning reasoning about the video content, but then use them to act or sort of to act and interact with the world and learn from these interactions. And to just to show an example, this is a video from our colleagues from LAS in Toulouse of a humanoid robot, which they have in the lab. And so at the moment, so we would like to now take some of these learned skills and transfer them on this robot and show that the robot can learn from a YouTube video to perform a particular action. And of course, so this is one ongoing project. For one, the robot does not, it needs to also see the objects in the world around it. So this is another ongoing work in this robotics direction, where this is one of the standard data sets, but we would like to obtain fairly accurate 6D poses of objects in the world. So 6D, so that would be the locations of objects and their orientation. This is one of the images from a standard data set with several different objects. Very difficult because they are textureless and very similar to each other, and there may be multiple different instances. So we've developed a method which hopefully will appear on arXiv soon, which can do this estimation very well, sort of much better on this particular data set than existing state-of-the-art methods, and what is combining information from several different views. Which you can imagine, you could be even a moving camera, which we don't study yet. And this is an example of output. This is so it assumes you have a known model of the object, and then you can recognize it in these different in the scene. And this is the 3D interpretation of the scene from these input images. And the goal is to really do it very accurately, so that you can then manipulate these objects and do just to see. So you can see some of the accuracy here. The objects are touching, and here. This example, the plug is actually plugged in the other one, so the accuracy can be quite accurate. The accuracy of the estimates can be quite good. So this I will show maybe a close-up of this. And the goal now is to sort of combine that, have some kind of to make it real time as well. It's currently not quite real time, and so that we can use that on the robot estimates the positions and of objects around it. And finally, of course, this is sort of in the direction of transfer on the the skills to a robot. So this is an example of input video, the estimate sort of interaction. And because we actually use the tool, we can then, rather than the robot and imitating the particular person, it can focus on the motion of the tool which we can transfer. And we can use that as an initialization to learn a policy here in simulation to perform some kind of a shoveling task in the simulation. And of course, learning this directly, how to move the balls from one side to the other in using reinforcement learning turns out to be difficult. But if one uses the initialization from the person, it becomes much easier. So this is sort of an example of ongoing work in that direction. So finally, to conclude, it is really an exciting time to be working in this area where, and I think we'll see sort of more application-specific constraint setups, but in general, it's sort of exciting to develop sort of models which would allow autonomous learning, reasoning, and interaction with the physical world. And of course, I think we'll see and need more collaboration between different research domains, like computer vision, natural language processing, as you saw before, but also robotics, speech, and of course, machine learning. So with this, I will finish here. Thank you very much for your attention. I'm very happy to take some questions.
Thank you, Joseph.
Thanks.
So yeah,
thanks, Joseph.
Thank you, Joseph, for sharing all this amazing work. Yeah, Humam, go ahead. Are there any questions from the audience?
Yeah, so I'll go through some of the questions. I will try to focus on the ones that got more likes, but if you guys find more questions that are interesting, please click the like on it. All right, so we'll start with one question from Juan Carlos Nieves. He says, for the general tutorial videos, caption descriptions can be temporarily misaligned to when the described action actually occurs. Do you attempt to realign the video and the captions during the representation learning?
So this relates to the, I don't know if I'll show this.
To the CVPR 20 paper, yeah.
Yeah, exactly. So this is kind of an attempt really to do this. We don't do any explicit pre-alignment, but we've sort of, our answer to this, exactly, we've noticed that. So I think it's a very good question, perfect question. And we've noticed that our estimate is roughly that 50% of the sort of video clip and language fragments are actually aligned and contain some kind of relevant information. But to improve that, we've noticed that, of course, sometimes it's mentioned in the nearby sort of captions of the video. So we've exactly one way to answer that, and we've sort of tried several different things, but of course, this is one, could be maybe others, is that we consider, and I will sort of show them looking for the video, we consider sort of multiple of these neighboring captions or fragments of that caption in the video and try to do this alignment in the loss during the learning. So only so consider multiple ones and pick the most relevant ones during learning in this contrastive, multiple instance contrastive loss. But it's a very good, I mean, it's one of the problems. Yeah, sometimes it may not even happen in the video, which is I think even worse.
I guess one related question to that from myself. The sampling of the negatives that you get in the NCE loss, how sensitive is the performance on the downstream task to that? And what kind of, let's say, tricks or hacks did you guys figure out on sampling that negative text?
It's again very good question. Yeah. So it's so we first in the ICCV paper, which is introducing the data set, we had sort of we had pre-learned the presentation, only learning the shallow kind of embedding layers at the very top, and there we found that the sampling and I don't have the exact numbers, but the sampling of negatives was important. And in fact, one of the things which we found in that work is that sampling negatives which were from so you have one instructional videos, which may be say 3 minutes long, And as considering negatives, which are from the same video but far apart, was important, because you may be doing, our interpretation was that you may be doing different things during that video. First, maybe washing the apple, then peeling it. And if you really want to localize that action of washing the apple, having negatives which show peeling apple, it was a good thing for localization. So that was really the sampling the negatives. How you do it we found was making a difference. Now, for the follow-up CVPR work, which we did in collaboration with DeepMind, we had much more computational resource. We wanted also learn the models from scratch. But there, somehow, in some sense, brute forcing this, sort of sampling more and more negatives in the contrastive loss, somehow overcame this issue. So at some point, if you have enough of the negatives, even if they are randomly sampled, this is sufficient. So I think that's kind of maybe the quick answer would be, if you don't have, if you kind of cannot have enough negatives because of computational resources, you may have to do some clever sampling. If you have enough resources, you can have a large batch size and a lot of negatives. You don't have to do that much clever sampling. That's our kind of initial take on this at the moment. That's a good question.
So I'll take next question from Aritra. I think this refers to the earlier part of your representation. He asks, how does the covariance matrix of the latent space looks like? Is it desirable to have disentanglement in this kind of latent space, considering the fact that task labels might have a lot of things in common?
So which part of the video, which part of the presentation?
I think
that would be?
This is the earlier part of the representation when you were talking about the latent space for the contrastive loss between the text and the video. So, and if I'm wrong, Ritra, you can correct me on the chat.
Okay, so maybe I'll start, and if there is any correction of this, let me know. So we have not. Okay, so maybe I think one way to answer this would be looking at the moment, our representation is of the language part. So in some sense, this is the language model somehow defines the label space, if you wish, right? So it's the language model is, so rather than having predefined vocabulary, one uses the language model to kind of define the embedding space. And the language model in this work is relatively still simple. Because what it is there's a sentence, individual words, which are embedded using some pre-trained word2vec. That's the part which we keep pre-trained part of it, which is then transformed, and then the key element is max pooled. So there is a kind of you take embed individual words, and then you max pool the representation. So when we talk about this representation, the way our intuition about it is kind of like a bag of words representation. There is not really sophisticated sequence modeling or anything like that. So it's really kind of on embedding space, but bag of words like representation. And this sort of defines the embedding. So it's in general, I think this embedding space is key. So having it somehow disentangled, maybe for verbs and maybe the nouns could be beneficial. Currently, it's kind of like so we may have a little bit of maybe disentanglement, which is from this pre-trained language representation, but it's nothing really sophisticated. It's kind of a bag of words. But of course, more recently, we are also looking into these much more powerful representations like BERT of language, which can be much more fine-grained. But I think this is ongoing work. I think it's trickier to work with those because, of course, this is a noisy, the input signal is noisy. But there is, I think, potential to really distinguish much more sort of fine-grained, say, vocabulary using those more powerful representation. But I don't think we are there yet. It requires more work. So I would say no explicit disentanglement to only what we kind of get from this at the moment, but it's an interesting direction for sure.
Indeed. All right, I guess we can take one more question. Louis asks, in the MIL-NCE loss, we have seen a major boost from pre-training if the downstream domain is similar to the pre-training domain. For example, UCOOC2. Would you comment on how to probe into what factors, e.g. the data domain, the data size, the training objective, the embedding space? Which out of these factors contributes to better transferability?
So this is again very excellent question. So we are still observing. I think, of course, there are benefits, and it's in the paper. We ablating the different components of the loss, and they are beneficial. But in the transfer, we are observing the effect of we call it a domain gap, if you wish, or there's definitely, depending how, and on a high level, I'll mention a few data sets. Of course, UCOOK2, in some sense, and I sort of show it as the prime example, but it's sort of closest to the how to 100 million data set because it's really instructional videos and cooking videos in some sense. There are other data sets which are also maybe instructional, but more bigger domain. Then there is MSRVTT, which is like YouTube videos, there is a bigger domain, and there is a LSMDC, which is movies, and this is even bigger domain. So I think we are definitely observing this effect of domain, this domain gap. When we transfer, the bigger the domain gap, the less well the transfer works. Now, if you fine-tune, if you allow yourself fine-tune, you can close some of that gap. It still seems that the pre-training is beneficial, and with the fine-tuning, and you can still get when you fine-tune, you still get a boost when you pre-train on this how to 100 million data set. But there is definitely this gap, and I think it's one of the key open problems which we are facing at the moment. How do we close this domain gap? How do we design representations which they transfer across domains? I don't have a good answer to this. But I think it's an important question to work on.
I don't know, we can take one quick question if Joseph doesn't have another.
No, it's okay. I'm fine. From my
Sorry, I guess we can take one quick question on the last part. Juan Carlos asks, let me find the question. So very interesting work on force estimation in the human-object interactions. Are there some examples of action objects that could be readily transferred to a robot? I guess shoveling or dumbbell lifting may be hard to test on a robot in a lab.
So actually, so we are trying to do that at the moment. So our goal is to. So I think I'm not. So we are collaborating with roboticists. So it's an exciting collaboration, across different research domains, and it's, of course, one can do different things. Yet, what I found, at least, and I'm sort of trying to convince, and I think we also agree with my colleagues on that. We're trying to find examples of tasks. So first of all, I think really the key benefit of our approach is that we actually model the tool. So one thing is that because we model the tool, we are hoping, and I think this is something we work on, that we should be able to demonstrate the transfer to very different robots. Because of course, if you just have a human, you may be able to transfer easily to humanoid robot. But how do you transfer to different robot morphologies? Well, if you model the tool, then and what happens with the tool, that may be easier. The second thing is that. Interesting are dynamic motions, and I think the shoveling is a relatively nice example of that because it sort of does require some, or may benefit from dynamics. And the third thing is we don't model quite yet, and this is one piece which we actually are focusing some attention at the moment, is that we don't model, as I said before, the interaction between the object and the environment. We don't model that, we don't extract that from the video, but I think that's where we're focusing the attention now, to actually do that on the reinforcement learning part, or maybe even have a more explicit kind of physical model on this. But I'm actually, for the shoveling, I'm hoping that to be able to demonstrate something like this on a real robot. We are show us some example of this task. I think hammering may be of course more difficult, but still it is task where actually some interaction with the environment and which sort of, I would say, highly non-linear interactions with the environment are exciting. Whether we are able to do that, I think, let's see. But I think that's one example which would be interesting. I think I was forbidden by my robotics colleague to do the scythe. They said it's too dangerous. The other things, they said we can maybe find some setups which would be workable.
Awesome. All right. I think this is all the time we have. We thank Josef again for the really interesting talk.
Thank you very much for the invitation.
And this recorded will be available on our website and on the YouTube and the Bilibili channels. So we will advertise that for people to watch who didn't have time to do that on the live session. Thank you, everybody, and please continue watching the rest of the workshop on our channel. And we will have in the afternoon the invited talks from 3 industry researchers. So stay tuned for those ones. Thanks, everybody.